find internal loads at D and just to the left of E, or E minus. All right, first step, typically we want to find the external reactions before we try to draw any of these internal cuts. So that when we make an internal cut, we're only left with 3 unknowns that we'll have to solve for at that point. Looking at this, we have a built-in connection at A, or a wall at A, a fixed connection. At C, we have a roller. So externally, how many reactions does this object have? How many unknowns externally will we see here? Right, we have 4, because at the wall we'll have an x component, y component of force. We'll have a moment at A, and then we'll have a y component of force at C. So there's 4 external reactions happening here, which makes it externally statically indeterminate. However, we do have a pin connection at B, where we can treat this like a frames and machines problem. So this is actually an internal forces problem inside a frames and machines problem. And the frames and machines problem we have to resolve first. Then we can go inside and start the new topic, or the new material, on the internal forces. So my free body diagram step already, I want to split this up into, I'm not making an internal cut, which is to say I'm not finding internal forces, but I am making individual free body diagrams of the members that I'm separating. Because in this case, I can separate it at B, which we're going to treat as a pin connection. So my first free body diagram, I'm going to take from A, the member that goes from A to B first, and model what's happening just to that piece of the member. At A, I have that built-in connection that I want to model. I have the AX, the AY, and an MA. At B, I have that pin connection where it's being pinned to another member. And like we saw before with frames and machines, I can arbitrarily assign directions to the pin reaction at B. And that's, so I have the external wall reaction, I have this connecting reaction with the pin at B, and then I also have a distributed load that acts from A to B, which in this free body diagram I can simplify like we did before to just a point load. It's a uniformly distributed load with a constant intensity, 2 kilonewtons per meter, and it acts over the entirety of A to B, which is 3 meters. So this is equivalent, in this picture, it'll be equivalent to a 6 kilonewton load acting in the center, 1.5 meters from either end. We'll come back to that topic of distributed loads when I get to the internal picture here, but we'll start with this. So externally, this is what this beam is going to look like. If I look at this picture, I have 5 unknowns here. So I'm actually going to hold back on writing equations and see if the second picture is going to be an easier place, mathematically at least, to start. Separating this out then, I can draw from B to C. I have that roller at C. And that internal pin at B, I've already assigned directions in my first picture, so I have to have equal and opposite directions in this one. And the beam from B to C has this 10 kilonewton force, but B to C doesn't know that there's a distributed load happening because that's happening on member number 1. So in member number 2, I just have to compensate for that point load here that's also acting in the center of this beam of 1.5 meters. And looking at free body diagram 2, I only have 3 unknowns in this picture. So I would say mathematically, it's going to be easier to start my equations with my second picture and then use that information to find the first picture. At this point, I'm still just solving the frames and machines problem. There's no internal cuts, at least through material. It's internal in that this pin connection is internal to my structure, but it's not actually internal to any member in my structure. In picture 2 then, if I start by summing the moments around B, I'll have 3 times Cy minus 10 times 1.5. in which case I can find Cy is 5 kilonewtons. In the x direction, I'll have a negative Bx, which means Bx must be 0. And forces in the y direction, I'll have a negative By minus 10 plus Cy. So that internal pin connection By is going to be a negative 5 kilonewtons. I have Bx and By, and now if I look at picture 1, there's only 3 remaining unknowns, so I'll be able to solve those pretty easily. In the first picture, I have Ax plus Bx, but knowing that Bx is 0, Ax must also be 0. In the y direction, Ay up minus 6 plus By tells me that Ay is 11 kilonewtons, pointed up. And the moments around A in picture 1, I have Ma, which I assumed was counterclockwise, the couple from the wall, minus 1.5 times 6 kilonewtons, plus 3 times By, which I know is negative 5 kilonewtons. So that moment from the wall at A is going to have a value of 24 kilonewton meters. And my assumption of direction was correct. It is going to be counterclockwise. Right, so now the new, more interesting piece, actually attacking what the problem is asking for, the internal loads at D and at E. So I'll start at D, make some more room here. And draw its picture first. Like we saw on Wednesday, since it doesn't say otherwise, I'm going to say that I'm always going to be making a perpendicular cut through that point. So if the beam is horizontal, I'm going to make a purely vertical cut through point D. And I have the option of taking everything to the left of my cut or keeping everything to the right of my cut. And actually here I have a couple more options. I could keep actually every part of the beam to the right. I could actually take just from D to B as well because I know what's happening at B from that previous step. So I have a couple, probably 3 different options here of what to do. But because to the left of D, just less is happening, I'm going to take everything to the left of D as my picture. I think that's going to be the simplest way to do this. But any of the methods would give us the same answer. On this piece of beam that goes from A to D, I have all those reactions at A that I found before, 11 kilonewtons up. The moment of 24 kilonewton meters. Acting at A. Ax turned out to be 0, so I just won't draw it in this picture. I'll jump to what's happening at the point I cut. So at the centroid of this beam, which I'll just draw as being in the center, I don't have enough information to actually know exactly where the centroid is, so I'll just model it here. Coming out from that surface, I have the internal normal force, P sub D. On this side of the cut, actually it should be facing down on this side, I'll have V sub D. And then by convention, M sub D I'm going to assume is counterclockwise. So on the right edge of a cut, V we assume down, MD we assume counterclockwise, and PD is going to be coming out from my surface. So the last thing I need to compensate for is how much external force is acting on this. Unfortunately, I actually just, let me bring this back up. So this was my section, or my member from A to B that I had originally. I took that distributed load, I simplified it to a point load, and I was able to use that to solve for those external reactions. What we want to be careful of is when we're drawing these internal section cuts through our member, is that we always refer back to the original diagram and not our simplified free body diagrams. Because if I make a cut through D here, and I say I want everything that's happening to the left of that, according to this simplified picture, that point load is not going to be there. But if I go back to my original drawing, my original diagram, where it's not been simplified, if I take everything to the left, I now have to include the amount of the distributed load that acts on this section that goes from A to D. So here where I simplify it to a point load, it's not including in this picture that amount of the force, but in this picture it does. So on the span from A to D, I have 1.5 meters worth of that distributed load that I have to include acting here. So again, I have to include 2 times 1.5 is going to be 3 kilonewtons. And then that part of the distributed load acts at the center at 0.75 meters. And that's the difference we see externally. Turning that distributed load into a point load is fine. It doesn't affect the reactions at A or at B. But internally, that simplification does matter. There is a difference whether this did have a distributed load or whether it actually had a point load. Internally, it makes a difference. Externally, this doesn't know, did this come from a distributed load or a point load? Those values are the same. But our internal forces are different between the two circumstances. So because it's a distributed load, it gets included, that piece of it gets included here. Because we did that first part and I solved for AY, AX, and MA, then this diagram only has 3 new unknowns that I need to solve for. In picture D, PD pointing to the right, AX turned out to be 0, so PD is going to also be 0. This piece of my beam is not in tension nor is it in compression, since I have a 0 value for the internal normal force. In the Y, I have that 11 up, that part of the distributed load down of 3, and then also down, I have V sub D. So solving this for V sub D, I should get a positive 8 kilonewtons. Again, that's according to this assumption that VD was down on this right-hand side. That's why I get a positive 8 kilonewtons. And if I take the sum of moments around the centroid here, by my sign convention or my assumptions, I say that MD is going to be counterclockwise, so positive. PD acts through the centroid, so it will not contribute to the moment about it. VD is going to act along through that centroid as well. I have to include that 3 times 0.75 minus 11 times 1.5. Negative 9.75 kilonewton meters. Yep, so we have 2 forces and we have that couple at the edge. D then is taken care of. So we need to look at what's happening just to the left of point E as our other picture. I make a cut vertically through point E and I can take everything to the right or the left. From this picture, there's less happening to the right of E, so I'm going to include that as in my free body diagram. There's the roller at C, which was CY we found previously, had a value of 5 kilonewton. And then through the centroid where I made that cut, I'll have the internal normal force, P sub C. This will have VC up, and this will have MC clockwise according to our assumptions for when we're cutting at the extreme left of the beam. So here it was down, we assumed, here it's up, here it's clockwise, here it was counterclockwise, PD coming out from the cut, PC also coming out from the cut. And we also have to be concerned here, because we're taking our cut just to the left of point E, because we have a point load acting on point E itself, if we're cutting just to the left of it and we keep everything to the right, that means that this picture will include at that edge the 10 kilonewton force. Again, that's the difference. If we were looking just to the right of point E and we took everything to the right, then this picture would not include that 10 kilonewtons. And this is going to affect the value of my internal shear force, whether it's in the picture or not in the picture. So there's going to be an immediate change in the value of my internal shear force just to the left of E versus just to the right of E. Any questions on the free body diagram for just to the left of E? Again, from step 1, we already knew that external force of 5 kilonewtons. So there's 3 things left we don't know, and then these are usually very easy to solve because every equation only has one unknown in it. So in our picture E, if I take some forces in the x, this tells me that the internal normal force at E, or just to the left of E, is still 0. In the y direction, I have the apply load negative 10, the roller is 5, and I assume VE is up. So the internal shear force I have in this picture at VE, I should get a newtons also passes through the centroid. So the only other thing I have is plus 5 times 1.5. So I get a value for ME, a positive 7.5 kilonewton meters.